All right, so now we're going to be looking at something called regression. So you've heard about regression in the course up to now, and we'll be focusing on linear regression, so it's very closely related to what we've just done on correlation. But before going there, I want to just do a very, very quick review of your high school mathematics when you looked at a straight line. So here we have a straight line, and there is the definition of the straight line. And what a straight line is a relationship between an x and a y. So for example, here are our axes. We put our x-axis this side, and we put our y-axis going up. And we relate, you give me an a and a b, that defines a line. What that means is you give me an x, and I can find the corresponding y for that x. All right? Now, what we'll be doing is, the reason is we're looking at this is, up to now, we've been estimating a single parameter, like the mean, or the standard deviation, or the correlation coefficient. We have just that single parameter. Now, we're going to be looking at estimating a line. And so here's the line. We want to estimate such a line. And the way we're going to be doing it, of course, is just by defining and estimating the two parameters in the line. Now, what are these? A is the intersect. So, for example, if you put x equals 0 into this equation, what you get that y is equal to a. So a is where the line crosses the y axis. And what is b? Well, if we start at a point here on the line and we increase x by 1, what happens to y? Y gets increased by this amount. That is b. So that's the slope. So b is the slope. In this case, it's also, remember, it was the tangent of the angle and so on and so forth. So we can dig up all our old notes about linear algebra, and we can dig all this up and review all this if you want to. But anyway, here is one example, and that line has an intercept of 0.75. So that means that this point here, I'm sorry, I wrote it the other way around. So this has an intercept of -1. So this line, so this point here is the -1. So that's the intercept. And it has a slope of 0.75x. And what that means is that every time we go across 1, we go up 0.75. So here's an example of a line. So A would be -1 and B would be 0.75. All right? And sometimes we call this the -x, and this would be the -y down here, and so on. Okay, so enough for the review. Now, why are we looking at this? Because sometimes we want to track things, say, over time, or as we get older, certain things go hand in hand. So we're back in the correlation domain, except slightly different. We'll come to that in a minute. So, for example, the WHO is much concerned about making statements about how we should be growing. So here's a typical generic picture, and this line is telling us how things should be progressing. This is over 1 year, 2 years, 3 years, 4 years, etc. How things, now what is that measuring? It could be height, it could be weight, it could be head circumference, whatever. And this is a study of how things should be going if things are progressing normally, or at the same time, that also gives you some bounds maybe to tell you about, be careful, if you're below this or if you're above that, you should be concerned and things are not going quite as normal. Here's an example. So here's the head circumference for age. You can get a number of these at that website, the WHO website you just saw on the previous slide. And so here's head circumference for age for girls. I chose this one because I love the color. It's very bright. Now, what this line here in the middle is the mean. So this is what the mean head circumference should look like as a typical little girl gets older and older. So she starts at birth, and so this is at week 1, then at week 2, then at week 3, and so on. So the head circumference, it's measured between here and here. You put a tape around the head about here, should be going up roughly like this. Now, what have they done here? They're actually showing you on this axis, they've shown you what the Z-score is. So we look at each age and we look at the head circumference minus the mean for that age divided by the standard deviation, because there's lots of people, lots of little girls at that particular age, and we calculate their standard deviation, and so we standardize things by getting our Z-score. So here's the Z-score, and so here's at -1, so these two lines are +1, -1, so there's your plus or minus 1 standard deviation at this particular age, or you could do the plus or minus 2, and of course, because these head circumferences are really normally distributed, very close to really normally distributed, we'll assume that this means that 95% of all babies, let's say at this particular age, 95% of them are going to have a head circumference in there. And then there's the plus or minus 3 for the Z-score, which means plus or minus 3 standard deviations from the mean. And so what we could do is we could use this. So for example, if the head is too big, let's say we're up here, then that defines macrocephaly. So we're talking about macrocephaly. And down here would be microcephaly. So too small. Now, the other thing to notice is that this stuff is all age specific. So for example, a baby is born and the head circumference is here. That's 34 centimeters. That's fine. That's the mean for a baby who's born. But if you maintain that same head circumference, but let's say at 13 weeks, now you're talking about microcephaly. So that's how we use these things. We make it very age specific. Making it age specific lowers the variance or the standard deviation, as we'll see in a minute. Because at birth, here's the standard, here's the 95% of them, whereas later, here's 95% of them. So if we forget the age, if you consider all of them, then they're between here and here. So you have a much bigger range if you ignore the age. Okay, but let me clean up all this mess here. So all right, so here is the Z-score, and it goes from -3 to +3. Now be careful, because this is wonderful, and what we did is we made it age specific. We calculated the mean to be age specific. In some places they don't do that, and at first, when I first saw this, I was a little concerned. So let's switch attention to osteoporosis, and what we're concerned about here is fractures, bone fractures. So for example, here specifically hip fractures, and this is what the WHO tells us are the numbers of hip fractures around the world, and we can see that it's climbing up tremendously. Be careful, because some of this is predicted. So because look, it goes up to 2025, but looks like this is for women and this is for men. So you can see it's a problem for both, but it's a much bigger problem for women. So let's just concentrate on women for now. Now, if we look at various parts of the body, we see that bone density is decreasing with age. So here are 4 different parts of the body, and you can see that in each one of them, with age, there's a decrease in bone density. So it's age-related, all right? And there's diminution with age. And so what they've tried to do is they've tried to use bone density to predict what would happen to a person, as I said here, specifically for women. So what the WHO, the World Health Organization, has done is define this quantity called a T-score. Actually, others have done this too. But here it is for the WHO. And what they've done is the usual way of standardizing that we've been doing up to now. You look at a person's score, and you subtract from that score a particular mean, and you divide by the standard deviation. Now, if you do it like we did for the, or how they did for the head circumference, then that would be a Z-score, because the mean they subtracted was the appropriate mean for that age group that you were looking at. This one here is not that. This is a T-score. They could do that. They get you a Z-score that way too, but this is a T-score, and what they've done here is they've subtracted the mean of a 30-year-old. So, for example, if we're dealing with women, this is the mean bone density for a 30-year-old healthy woman, a typical 30-year-old healthy woman. And then they come up with a T-score that way. Now, why are they doing this? Well, okay, once they do this, then they create this categorical variable. Remember the categorical variables? With 4 levels: normal, low bone mass, osteoporosis, and then severe or established osteoporosis. And it's all based on this T-score. And so if the T-score is between plus or minus 1 standard deviation, so if we're 1 standard deviation away, at most, less than 0, then that's just normal. Whereas if we're between -1 and -2.5 standard deviations, then that's called low bone mass. And if we are less than 2.5 or lower, then that's what we call osteoporosis. And then if you've had 1 or more fractures, you're below there, and you've had 1 or more fractures, then they call that severe or established osteoporosis. Now, if we'd kept these standard deviation definitions of our categories and kept this up here, if we define it with the appropriate mean and come with the Z-scores, then we'd have always the same proportion of women in each category, because the bone density is approximately normally distributed. But no, because we're shifting things, we're looking at minus the 30-year-olds, things change. So, for example, here's what happens. You see, here's for 50-year-olds, here is the bone density, has this distribution like this. So if we chop off the, let's see, 1, 2, 2.5, then we've got a very small percentage down there. Let me not do that. Now, if we keep this, you see, the effect of always subtracting the same amount means we keep this line fixed. But the bone density is getting lower and lower and lower. So this is shifting. As we get into the 50s, this shifts to the left. So if you're keeping this constant, you're chopping off more and more and more and more of the population. So they're linking bone density with osteoporosis. And they're doing it in such a way that as age increases, you're getting more and more, by definition, with osteoporosis. And they chose to do it this way because they argue that the osteoporosis is increasing exponentially with age, and this is the way of doing it. Okay? So it's not that they're just trying to scare you with these T-scores. There is some method behind the madness here. And you can see that this is just for vertebral fractures, men and women, and you can see that with age, these fractures, the number of these fractures increases. Okay? So what they've done is they have changed it so that these quantities in here by age, so for example, in the normal group, at age 25, 84% of the women are in that group, normal. whereas by age 50, 66% are, by age 65, 40%, and so on. So if you look at the osteoporosis, just by aging, you can see that the percentage goes up from 1% up to age 50, and then age 65 is 13%, and it's 27%. So what you've got is you've got these distributions here going down. So these distributions are sort of going down. Now, they tricked you a little bit, because be careful, these are going in the wrong direction. This is getting smaller and smaller as we go to the right. We're not accustomed to seeing this. We typically have it the other way around. So think of looking at this from this direction here. So this is the left. But anyway, you can see that this cutoff is just the same, but the distributions are shifting. Okay, the distributions are shifting with time. So as well, you can see what happens here. But the interesting thing is, one thing you want to carry off from this is that at every age group, there is a distribution. At every age group, there is a distribution. So this is where the complexity comes in regression, is that at every age group, we've got a distribution. Now, you've seen this. You've seen this before. I showed you the sex ratio as a function of gestational age, and then that is an example of regression. So the idea is, as age changes, you're just looking at a different slice. You're looking at a different set of people. But each one of that set, each group in that set has its own distribution. All right? And so this is the idea behind regression. And what it is we're looking at the distribution of one variable, call it y. So for example, osteoporosis, or we looked at head circumference, as the other variable, call it x, which might be bone density or age. And we're looking at the distribution of one of them, y, as the other one is kept fixed but varies. All right? So the y is sometimes called the response variable. So how does the response variable vary as we change our independent or explanatory variable? So as age increases, how does the response variable vary? We're looking at a particular characteristic of that one variable, and that is the mean. So we're going to ask, how does the mean of y vary as x varies? And this name regression is due to Galton. And actually, he originally called it regression to mediocrity. But in those days, mediocrity meant mean. And what he was looking at was that if you looked at children of parents, so for example, if you looked at sons and you looked at the height of a tall man, so if you have the tall man and you look at his son would also be tall, but not as tall as the father. So he would be a little bit shorter, so he would be closer to the mean, closer to the average. So you had this regression to the mean. And also for the short man, his son would be short, but taller than the father. So you would regress to the mean. So that's the name, the regression to the mean. Now, it's different from correlation, although you'll see shortly that it's very closely related. It's different to correlation in that it's not symmetric. In correlation, we had x and we had y, and they were correlated with each other, and there was no idea of dependent or independent variable or response and explanatory variable. Here, we've got the notion that one of these, x, is the one that maybe you vary, and then you measure y and see how it's affected by the x. All right? So here it is. So here is the definition of regression. If we're given two variables, x and y, then what we do is fix a value of x. So fix a value of x, and look at all the y's for that value of x, and take their mean. Then the regression line is really a regression line. We should call it a regression line. We shouldn't just say regression. It's a regression line. So the regression line of y on x are the means of the y's for the given x's. So you give me an x, I'll get the mean of the y's, it might be this. Okay, so that's the mean of the y's. Then give me another x, I'll get the mean of the y's, and then join that up, and that line is the regression line. Okay, it's a function of x. It's not a function of y, because you're going to average out the y's. So the regression line is a function of x. So, for example, here we had the bone density, and so here's the bone density distribution for the 50-year-olds. Well, there's the mean for the 50-year-olds. Here's the mean for the 50 to 59-year-olds. Call that 55 if you want. Here's the mean for the 65s. Here's the mean for the 75s. Okay, and here's the mean for the 80s. If we can draw a line like this through those means, then that line is called the regression line. So that's the regression line. Okay, so think of all those normal densities sticking out 3D, and then that this line is going on the floor there. That is the regression line. It's the mean for given x's. So here are my x's. So for x equals 50, there's the point on the line. I've cheated a bit. They call this 55, let's say. But then that's the mean for 55, say, and so on. But that's the idea behind regression. How is this line going up? So for example, here's an example of such a regression line. So what I've done here is I've looked at life expectancy. So go back to the life table and look at life expectancy as a function of x. So for example, if we zero in on 10-year-olds, then we go up here, and that's about, what, 63 or so. So for the life expectancy for a 10-year-old is another 63 years of life. So that means if we followed those 10-year-olds forever and ever and ever until they all die, on average, we'd have to wait 63 years. Same thing for 40-year-olds. For 40-year-olds, we might have to wait 38 years. Okay, so the average survival of 40-year-olds, for people who have reached 40, how much time on average before they die? And the answer is, about 38 or so. So then draw a line through all that, and there is our regression line. Now, this line has a little bit of a flat spot there. That's a teething situation we've always talking about. Then it's pretty straight. I would argue that it's pretty straight up until about age 60, even maybe a little bit beyond that. And then it curves. Like this. We are going to be focusing on straight lines. So we could say locally from about age 2 to age 60, we've got linear regression. So this part is linear because it's a straight line. Here's another example. Now this is with the group where I showed you the sex ratio. This was with the 4.5 million births, singleton births in the US, 4.2 million, and this was back in 1991. And what this is if you looked at the gestational age, so for example for gestational age 20, so look at all the babies born that year at gestational age 20, then what we look at is the mean mother's age for those kiddies, and there it is. So it's about 25.6 or so. Okay. Then we look at the kids who are born at 21 weeks, and there it is. So what these dots here are the means. I've done also plus or minus 2 standard deviations. So once again, these plus or minus 2 standard deviations in here are tiny, 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 because we had 4.5 million observations. So we can see that most of us, as I said before, most of us are born around in this gestational age. It's interesting to look at the mother's age as a function of gestational age of the babies born. Now, this sort of looks backwards. This sort of looks like in reverse, because remember I said to you it's the x's that should be the independent variable and the y should be the dependent variable. So maybe you would argue that we should interchange these two axes. Now when we do that, we get this kind of picture. So when we do that, we get this. Now there are very few mothers up here. This was back in 91. So there are very, very few mothers up here. So this is a little bit topsy-turvy, a lot of variability, because it's not based on too many observations. Whereas this looks like a very, 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 very smooth regression line. So there's the regression line there. You know, nature is smooth. And so one tends to believe smoothness when one sees it more so than variability like this. But anyway, this, you could argue that this is sort of linear, and here we sort of have linearity. The whole regression is not linear. This is not, I'm not saying that this is linear regression, but if you're focusing on particular ages, then you could look at linear regression. I can't spend this course teaching you about regression. I could take a year doing a course on regression, and we only have a few hours here. So we're going to focus in on linear regression. So we're going to assume that we have straight line regressions. And there's enough in there to whet our appetites to maybe bring you in for another course. But that's where we'll be looking at.